In this video, we're going to go through the solutions for your test 2 review. If you're after a particular solution for a particular problem, the timestamps will be in the description of this video. So for question number 1, they're asking us to check out this graph of an exponential function on the right-hand side. We're asked to state the domain, range, and horizontal asymptote. And to do that, we're going to be using interval notation. And so let's get after it. So right away, we'll notice that as far as the domain, all of the x values, there doesn't appear to be any restrictions. I don't see any vertical asymptotes here. So what I can assume, especially with those arrows pointing off to the left, that off to the left, we're going to go off to negative infinity for the domain. And then off to the right, if you notice the arrow on the top right there, it looks like it's kind of slightly slanted. So we know that it's going off to positive infinity as well. Again, we don't see any vertical asymptotes, so we don't see any issues in the domain. And then, of course, for the brackets, we're going to use rounded because this is going off to infinity, and we'll never actually get there. So no hard brackets for infinity. Next, we're checking out the range. And so in the similar mindset, right away, we'll notice that there appears to be a horizontal asymptote here. And we might actually just write down what this is, right? It looks like we could best describe this by saying y is equal to -3. That would be a good descriptor of this horizontal asymptote. Oh, and in fact, we actually need to answer that. So I can go ahead and put that down now if I like. Y equaling -3. That would be the best way to convey that information to somebody. And so the horizontal, yes, the horizontal asymptote will come up when we talk about the range, because notice I can get as close as I want to -3 for all of the outputs, but it doesn't look like I'll ever actually equal -3, right? And that would be the lowest value that the range could go to. And so actually I need to put a bracket possibly there to convey that, right? I'm getting as close as I can to that horizontal asymptote. And then as far as the largest value, right, when we look up towards the top of this function, again, we see that arrow and it's kind of just pointing off to the sky, right? So it's going off to positive infinity on that one. All right, and they say that stating the answer is sufficient. No work need to be shown, so we're all good here. Moving on to question number 2. I think the big idea with this one, we're supposed to create a table and sketch the graph of the following function. And they tell us that we need to at least use 3 input values. Makes sense. Right away, I would suggest picking nice points here if you can, because it's up to you on what points you'll plug in. Usually we'll have 0 as one of those points, so I'm just going to go ahead and plug that one down there. That is a nice point, and it usually is something that we'll plug in. -1, I think, would be okay for a point, just to have something on the negative side. And then I could just do +1, but I might do +2 just to mix it up. But again, choose whatever points that you feel like are the nicest. And then let's check it out. Let's go ahead and plug those values in that we chose. So I'm going to be just plugging this into the function f of x, right? So anywhere there is an x, I'm plugging in this -1. So it happens to be up here in the exponent. It's an exponential function. And so we're going to go ahead and solve this. So it calls on a definition on what a negative exponent does. The negative exponent, you can think of it as kind of, if it's in the top here, like 2 to the power of -1, we're going to put that 2 into a bottom of a fraction, and that would become 1/2. So let me go ahead and write that. I'll kind of invade my graph for a second, and I can erase it though. But I just wanted to show you that's what I'm talking about with that -1 exponent. It kind of just puts that value down into the bottom of a fraction. So 3 times 1/2 would be the same as saying 3/2, if you'd like. and then we're subtracting 4 from that still. We might actually go ahead and just rewrite 4 with the common denominator, right? That 2. And so that would be best represented, I think, as 8 over 2. And so if you just add the numerators, right, because our denominators are the same now, we'll get negative 5 over 2. If you're using a calculator, you might have come up with like negative 2.5, I believe is the same. So go ahead and put down whatever result that you have there. Okay, so on to the nicest point to evaluate. When x is equal to 0, we're going to plug in that 0 wherever there's an x in our function. And this calls on another definition that is very useful for us. Anything raised to the power of 0 is actually equal 1. So it's a really good choice for your exponent value because 2 to the power of 0 is just equal 1. And if we multiplied 3 times 1, we would actually just get 3. So this just simplifies quickly to 3 minus 4, which of course, if I only have 3 and I take away 4, I'm going to have negative 1 left. Great. Moving on to the last point here to plug into our function, wherever there's an x, we have 2. So we're going to go ahead and do 3 times 2 to the power of 2 minus 4. Okay, and so this is where we're going to have to do the repeated multiplication that the exponent is calling on. 2 to the power of 2 is the same thing. It's just 2 times 2. And so we're going to get 4 as a result. So I'll go ahead and write that down. Okay, and then 3 times 4, we're going to go ahead and do the multiplication before we do that subtraction. 3 times 4 is equal 12, and then we're subtracting 4. And if you do that, we'll get 8 as a result. Perfect. Okay. So I've completed my table. At the minimum, I was supposed to evaluate 3 values. Please, if you need more, go ahead and create more points. The point is to have some clarity on what this graph looks like. So, if you need more values for your table, go ahead and keep going. One of the things that could be helpful for us as we're graphing this at least will be the horizontal asymptote that we know exists for exponential functions. So we'll definitely have to consider that. Let me go ahead though and at least plot these points to begin. So our table, right, gives us the points that we can plot. So the first one here is x equaling negative 1. Y is equal to negative 5 over 2 at that point. And let me see here. So we're going to go to the horizontal axis, go to negative 1, and then go down negative 2.5 or negative 5 over 2. Let me go ahead and maybe I'll pick some different colors here, have that stand out. Okay, so that's our first point. Okay, our next point starts at the origin at 0, and then we move down in the y-axis to negative 1. We're living right there. Okay, and the final point that I have in my table is 2 on the x-axis, and then all the way up to 8 on the y value, just like that. So we really see the exponential growth of this. So I talked earlier about the horizontal asymptote that we know exists. It actually was seen, I believe, if we kind of scroll back up to question 1. Note this existence of this horizontal asymptote. And if you've been studying exponential functions, you know of that existence. We could actually call on some of that information that you might have with you. The parent function of this, it might look like a times b to the x. You might find that familiar. I think that will be coming up later on in this practice exam. So here, the horizontal asymptote in this scenario for this parent function is actually y equals 0. And so we can actually take that and build off of that to know what the horizontal asymptote here is. It actually is going to be this value on the end. So that probably isn't new to you. I'm sure you've heard this already in your class. So that's our horizontal asymptote. And before I start sketching in the connecting these dots that we've plotted, I'm going to go ahead and draw that horizontal asymptote at y equaling -4. I'll do my best to do this quickly. Right, something like this. Right, and I might even specify y equaling -4. Okay, so let me get rid of this work we drew over our graph and get back to that color I was using to plot this. All right. And so, do your best to connect these dots. Since this is an exponential function, it kind of follows this nice curve that we've seen before. And, this horizontal asymptote is pretty helpful for us because we kind of use it as a guide if that's what this function is gradually trying to get to, but it'll never actually get to. Great. Okay. And so this is actually really helpful. Because the domain is asked of us next. So as we did in question 1, the domain, we're kind of asking what are the x values that you can plug into this function. I don't see any vertical asymptotes, no holes in this function. So as we probably are well aware, exponential functions, we can go from -infinity off to +infinity. And again, those brackets are rounded because we never actually can equal infinity, which actually this reminds me, I should probably add some arrows to the end of this, right, to emphasize that point. Perfect. Okay, so on to the range for this function. This actually is very helpful. We already have noted what the horizontal asymptote is. We have a horizontal asymptote at y equaling -4. So notice that the lowest this function can get is it can try all it can to get to -4, but it's never actually going to equal -4. So the leftmost value in my interval notation for the range is going to be -4. And then we're going to do a rounded bracket because, again, we can try all we can to get to -4. We'll never actually get there. Um, and then the rightmost value, we're thinking about the greatest value that comes out of this function for the range. And we see that arrow that we just drew in on the top right there. And it's just telling us, hey, it's going off all the way to infinity, right? Perfect. Okay. And then close it off with a rounded bracket again. Okay, so it looks like we've answered all of the questions or all the parts for question 2. And, you might label your function to be f of x. I think that might be helpful. You could do some x and f of x on the axis. In fact, I could even specify, I guess it is stated here. So this would be above and beyond what we should be doing there. But that looks wonderful. A nice labeled graph. Okay, moving on to question 3. Question 3, it's very similar to what we were just asked in question 2, except for now we're dealing with a logarithmic function. And so right away, what we did in question 2, where I was describing, maybe we could pick some nice values to evaluate into this function. So we're going to do the same here with this logarithmic function. I'm going to call on some definitions that we should have memorized, or at least on a note card if we can. And it's first one will be that log base b of 1 is equal 0, right? And then the next one is log base b. And when I say b on these, I mean any value, right? Log base b of b, I suppose any value greater than 0, right? Um, is equal 1. Okay, so if we use these as our kind of guiding light for the selection of our points, we see that in our function, the argument or the thing inside of the logarithm is x minus 2. So my goal maybe for the choice of my first point would be x minus 2. I would want to choose an x value such that this would be equal to 1. So I could apply that first rule. And then the next one, maybe I'll say, okay, x minus 2. Our base here is equal to. So those would be my two possible ways of going about this. And then, if you can see what x is equal to, or if you need to solve for x, that's cool too. First one, you'll just add 2 to both sides. So 2 plus 1 is equal 3. And the same story down here, except we're adding 2 to both sides, and we get 4. Okay. So again, your choices of x's could be different, but I'm going to choose x equaling 3 and x equaling 4. Okay, and so now I'm going to be able to evaluate these values, 3 and 4, into the g of x function. And so let's see what that looks like. So I got the coefficient of 5 on the outside of my logarithm, log base 2, and anywhere there's that x in our function, we're going to plug in 3. So it's going to be 3 minus 2. And 3 minus 2 is equal 1. So I'm going to go ahead and just jump to that. And so what we kind of talked about at the beginning is that any base of a logarithm, when we're evaluating 1 into it, is going to be equal 0. And so this guy just becomes 5 times 0, which any number multiplied by 0 is actually just equal 0. So that's why I chose to use these rules, because it just kind of simplifies our process. Okay, and so for plugging in 4, right, again, I have the coefficient 5, log base 2, and for my argument of this logarithm, I'm plugging in 4 into my x position. So I'll get 4 minus 2. 4 minus 2 is just equal to, right? Just like that. And so notice that we have, again, this scenario where we have log base b of b. In our scenario, it's log base 2 of 2. But regardless, that will be equal 1. Log base 2 of 2 will be. And so we'll have 5 times 1, right, which is just equal 5. Perfect. Okay, and so let's see. Before we go, actually, let's go ahead and just plot these points. I'll change my color again, have those stand out. And so my first value here is when x is equal 3, right? My y value, or the output, is equal 0, so I'm living on the x-axis there. The next value is when x is equal 4. The output value looks like was 5. So I'm going to 4 on the x-axis and then going all the way up to 5. There we go. Okay, and so we might remember some things about logarithms, right? Um, Maybe if I was looking at this as far as what does the parent function look like, or what in general, like we can plug into a logarithm. So if I just had y equaling log of x, for example, maybe thinking about this for a second as a simplified scenario, we should know that the argument inside our logarithm always has to be greater than 0. And so in our scenario, right, we have for our argument inside our logarithm, we have x minus 2. Again, x minus 2. So we can actually do something similar, right? And we want to make sure that that value inside our logarithm is always greater than 0. So we're going to say, well, x minus 2 greater than 0 is going to be our restriction. And we can solve for x. So x, if we add 2 to both sides, x has to be greater than 2. So this guy, right, is a restriction on our X values. And remember, our X values are associated with our domain. So I'm glad that we did this, right? Because I think they're going to ask us after we graph this about the domain. So what I can do with this information is actually when X is equal to, this is going to be my vertical asymptote. I'll do my best to try to draw a dotted line for us. And we might label this, maybe I'll put it up here, X equaling 2. That's our vertical asymptote. Okay, let me switch back to the color we were using for this graph. Um, and so logarithms, right, they kind of follow this similar pattern to exponentials, right, because they're the inverses of exponentials. And so we know that it's going to, as it goes down, it's going to get as close as it can to the vertical asymptote. And then it's going to kind of come up like this. And I'll do my best. We might consider evaluating more points so we have a better idea of what's happening. We know it goes off in this direction, put an arrow at the end, goes off in that direction. We'll put an arrow at the end. Okay, and so that would be my best bet on what this graph looks like. I might throw X here for the X-axis and G of X here for the vertical axis. Okay, so they're asking next for the domain. We're asked to state it. Um, Again, note that there's a restriction on the X values that we can plug in here, right? We spotted earlier that X has to be greater than 2. And so that means for us, right, we can go to the left as much as we want with the X values, but we have to stop at 2, right? So we can get as close as we want to 2, and I'll emphasize that with a rounded bracket on the left-hand side of our domain. And then it doesn't look like, right? We see that arrow pointing off to the top right. So we can go off to positive infinity, get those values as big as we want. Okay, and so now thinking about the range, I don't see any horizontal asymptotes. Um, so no issues as far as the range, the output of this function. Um, in fact, we have that arrow that points off to negative infinity. And in the top right, again, we're going off to positive infinity for the outputs of this function or the range. Perfect. Okay, and so I think we got everything here. Let's go ahead and move on to question 4. Question 4 is talking about some interest, money borrowed, and it's at a rate given. So right away, I think for this one, we are going to use this equation. So A of t, right, is equal to P times 1 plus R over N to the N times T. So you probably saw this as you're approaching this problem. You're thinking, okay, that's the equation I'm going to use. Obviously, you don't know what P, R, or N are yet. We got to read the problem to get that. But when it comes to compounding interest, this will be the equation that we use in general. And so let's go ahead and detail out the information needed here. So Jenny borrowed $8,000. And so that's going to be our P value, right? So maybe I'll write that down. I have the recipe above. Let me write out the ingredients. So P is equal 8,000 at a rate of 13%. So our R value is our interest in a decimal form. So what you can do is you can take that, 13% and divide it by 100. Some folks like to see the 100% just to know, hey, those units are canceling, either way. So this will just move the decimal place over 2 places to the left, and we'll get 0.13 for our rate. And then what else is going on here? So assuming she makes no payments, how much will she owe after 8 years? So in general, our T value is going to be the time and the unit of years in this problem. So we'll have 8 there. Okay, so let's get into part A. They're telling us it's compounded annually. So in this scenario, what we'll do is we'll say, okay, in this case, right, the number of compounding periods in a year will be our n value. And since it's compounded annually, we're just going to say n is equal to 1. So let's see what this looks like, right? A would be equal our p-value, which is 8,000. We're going to do 1 plus r over n. And so since n is just equal 1, it's just 1 plus r. And since r is equal to 0.13, we get 1.13 inside our parentheses there. Okay, so we're going to raise this to the power of nt. Well, again, n is equal 1, and our t value is equal 8. So we'll just get to the power of 8 like this. All right, let me flip to my solution. I punched this into my calculator earlier, and that's what you would be doing here. Okay, so my calculator just straight out gives me this value, 21,267. And your calculator will probably do the same. It's going to give us, a bunch of decimal values. So just wanted to show you what you might be seeing in your calculator, something like this, right? And then it's up to us to interpret this, right? Since we're talking about money, right? That would be the output of this, right? So, that A value is the account value after 8 years in our scenario. So A would be equal to this this value that we came up with, but we can round it, right? You can round it to whole dollars if you want. I don't think it specifies, but I would probably round it, right? Give them more information and say maybe this, right? Rounded to 2 decimal places to talk about like cents on the dollar kind of thing. So there would be the answer for this. Okay, so moving on to a scenario where we're compounding monthly, and maybe I can get the information in the same screen here. So now we're compounding monthly. So, remembering that n is the number of compounding periods in a year, since we're doing monthly compounding, that would be 12, right? Number of compounding periods in a year. So here, n is equal to 12. So, same equation that we did in part A of this problem, but now our n value is equal to 12. So let's go ahead and write that out. A is equal 8,000 still. And then let me go ahead and write this one out. I didn't do it on the last one, but let me spell it out for us. We're going to do 1 plus r over n. So our r value was the 0.13. In this one, our n value is going to be equal 12. Just like that, close parenthesis. And then this will be raised to the power of n times t. So our n value is 12, and then our t value is 8. So just like that. Okay, and so when I punch this into my calculator, let me get back to my little solutions here. It's going to give me, again, that kind of long drawn-out number, 22,507. That's a 7. And then my decimals are going to do something like 0.49952229, something like that. And we can just do something similar that we did in part A and round to the second decimal place. So we'll get, and also adding the units too. I guess that was something I didn't highlight in the last question, but making sure that we're adding units, right? Because we are dealing with units. So that would be the good answer for part B. Okay, so part C, we're going to do something a little bit different for this one. Since the interest is being compounded continuously, That should be sending off bells in your head of the equation changes in this scenario, right? We're going to use this A pert. You might be heard of it referred to as that, but A pert. So the values are similar, right? We know our p value. We know our R value, that's our rate as a decimal. And then, we know our T, our time in years. So let's go ahead and put this together. Again, we're going to use this equation for compounded continuously. So A is equal, the p-value was 8,000. And then E is just a number, right, on our calculator. And so we'll put that there. And then our rate, again, was 0 point, if I'm remembering it right, 0.13. And then our T value in years was 8. So we'll put that up there. So it looks like when I put this into my calculator, I got 22,633. And then I got a bunch of decimals here as well. You obviously, you can write down whatever you wish. I just wanted to show you kind of what I'm doing with that raw data that my calculator gives me. So here, I'll probably round to the second decimal place again, right? So $22,633, and I'm going to round to 74 cents on this one. Perfect. So that would be everything for question 4. Let's move on to question 5. So question 5 is talking about Mia, and she's deposited some money into her account with this interest rate. It's being compounded semi-annually, so we'll get to what that means in a second. Assuming that no withdrawals are made, how long will it take for the investment to grow to this amount? So believe it or not, we're actually going to be using the kind of same equation that we were using in the last problem, question 4. So I'll go ahead and write that down, right? This is going to be equal to, or sorry, A is going to be equal to P times 1 plus R over N to the N times T. So that looks familiar from our last work. So this is the recipe for what we're going to do. Let's go ahead and talk about the ingredients here. Our P is our principal value. That's the amount that Mia deposited initially. And so that's 3,000. Our R is the interest rate, right, as a decimal. So we have 9.8. We're going to divide that by 100. Of course, we know that this moves the decimal place over 2 spaces to the left, right? So hopefully I did that correct. You can check my work. And then let's see, what else do we have here? We need our in value, and that was the thing I was talking about earlier. Well, our in value, right? That's going to be the number of compounding periods in a year. Compounded semi-annually is actually indicating that there'll be 2 compoundings a year that will be compounded semi-annually. So n is equal to 2. And then our t value is actually what we don't know, right? So maybe I'll put that down here and say, I don't know. That's what we want to know, right? And then they actually give us, in the second part of this, says, assuming that no withdrawals are made, how long will it take for the investment to grow to this amount, 4,614. So remember that this A value, right, represents the account value after time t, right? So here, this will be different, I think, than question 4, and that we have that A value given to us, right? That's the 4,614 that Mia is after. So it looks like we have the recipe and we have the ingredients. Let's put down our updated equation and see what's going on. So I have 4,614 again for my A value. The principal amount she deposited was 3,000. And then we have 1 plus our R over N And so our R value was this 0.98. We'll divide that by our N value, which was 2. And then we're going to raise it to the power of our N value, which was 2 times T. And we don't know T, if you remember. Okay, so this is great. We have an equation and we only have one unknown to solve for. Um, it's not what we're accustomed to. Maybe we've done linear equations with one unknown, but this is an exponential with an unknown. So we want to know what this value is up here in the exponent. So, spoiler alert, we're going to be using logarithms to gain access to that exponent. We'll first have to kind of do at least one operation to get to a place where we're going to be able to use logarithms. So the first step I'll do here is divide both sides of this equation by 3,000, right, to get rid of this coefficient out front, right, because 3,000 divided by 3,000 is just equal 1, which is a favorable result. So on the left, we'll just get this 4,614, right, divided by 3,000. And then those 3,000s just go away, right? We don't need to write the 1 if we don't want. It's assumed. And so we get this 1 plus, let me go ahead and give myself some more room here for what we're about to do. So I have 1 plus 0.098 divided by 2. And you normally would have this to the power of 2t, right? Let's go ahead and write that in. But I'm going to go ahead and take the log of both sides of this equation. And, just for fun to change things up, I'm going to use the natural log. You can use log base 10 on your calculator. It just shows up as log. But I'm going to do natural log or ln, right? And if I'm doing the natural log to one side of an equation, I have to do it to the other, right? Keep that relationship the same. So the natural log or any logarithm has this cool property in that the exponents, right, will come down and plop right down here and become the new coefficient of the logarithm. So let me go ahead and update our results, right? That indicates to me that 2t will now be on the outside of the exponent position. It'll be a coefficient. Everything else is going to stay the same. Try not to change that decimal value on us. And then we'll still have this equal to the natural log 4,614 over 3,000. Great. So this is wonderful, right? Because now we're in a scenario we're very familiar with, right? Our value that we're trying to solve for, this t, is now just a coefficient hanging out in front of this natural log. So you might imagine the next step here is we're going to just undo the multiplication that's being done to t. I can actually do both at the same time. T is being multiplied by the 2 on the left there, and then this natural log on the right. So if I divide both sides by those values, they'll kind of cancel out on the right side, and I'll just be left with t. And I'm just going to reorder this, right? Put the t here, and then so the left side initially was that natural log of 4,614 divided by 3,000. I'm putting it way up here because I have to divide everything by, well, there was the 2, and then there's this other natural log, right? 1 plus 0.098 divided by 2. Sorry, my handwriting is getting a little sloppy on this edge here. Okay, and so let's think about this, right? I don't know what the natural log of these values are. I'm going to go ahead and use my calculator to approximate this. And so when I punched this into my calculator before, right, t was approximated. Well, I approximated t, so maybe I'll use these squiggly brackets, right, to 4.5, right? Um, it's helpful to just take a second. What does T represent? Well, T is time. Uh, it's not quite obvious, but T is time in years. So I'm going to go ahead and drop the units here. And then you might write a sentence out if you want, but this would be your time in years, 4.5. So that's how long it would take Mia's account to reach 4,614. Okay, so let's move on to question 6. Question 6 is talking about a table of ordered pairs that represents an exponential function. And they're telling us to write an equation for the function and to show our work. Um, so if you've been doing this, right, if they give us the initial value, right, that's usually when our independent variable is equal to 0. And so that happens here, right, in our table. That's an excellent point to use. Let's go ahead and let me write down what the kind of parent function of an exponential function or what exponential functions look like in general, right? Something like this. Y is equal to a times b to the x power. We could write f of x. Maybe I'll do that, right, to emphasize the idea that this is a function, whatever you choose to do, though. Okay, so yes, as I stated, it's really helpful to have this value when x is equal to 0. We can use that to our benefit because this parent function, f of x, is equal to a times b to the x power. Um, you might already know that the a value is the value, the initial value, right? And so we could just right away say, well, a is equal 12. That would be the output when x is equal to 0. But let me show you how to do that if you don't remember this rule. So again, it's very useful when they give us an x value of 0 for an exponential function. So the output is 12. That's the y value. And then we'll just do a for right now, and I'll show you that that equals 12. And then we'll have our b value. And again, we're using the x value of 0. So earlier we talked about this, right? Anything raised to the power of 0 is actually equal 1, right? So in this scenario, we actually have, well, 12 is equal to a times 1, right? But a times 1 is just equal a. So it was a pretty simple, one step thing to just show this idea that a is equal to 12. Okay. And so our next choice of value, you could actually pick any of these. I think I'll go ahead though and pick the one next door just because raising something to the power of 1 is a nice little um, thing to do here. So our y value is equal to 48, right? And the y value is equal to a times b to the x. In our scenario, we found that a is equal to 12, so I can fill in that information. I'm actually after my b value, right? So I'm going to plug that just b in for now. And then b is being raised to 1, the power of 1. So here's another, great little definition to have down, right? B to the power of 1, any value b raised to the power of 1 is actually just equal b. So we would actually just have b in this scenario, right? I don't need to write the power of 1 if I don't want to. And so b is just being multiplied by 12 on the right-hand side. I want to know what b is. So I'm going to actually divide both sides by 12, right? So this 48 divided by 12. And again, I would have 12 over 12 over here as well, but that's just equal 1. Okay, and so let me see, right? What is 48 divided by 12? If you grab your calculator, if you know, that's going to be equal, what is that going to be equal? 4? There's 4 12s in 48. And so that's what our b value is equal to, right? Because we said 12 over 12 is equal 1. We're just left with our b value on this one side. Let me make sure that's not looking like a 6. Okay, and so we actually just gathered all of the ingredients, and we can just tell your instructor now the equation, is equal A is 12, B is 4. Make sure to write the exponent there, and we'll throw out the f of x out front kind of thing. So f of x is equal to 12 times 4 to the x power would be the exponential function that describes the relationship given in the table. Okay, moving on to question 7. Question 7, we can already see question 7 just has a bunch of logarithms, and we're asked to evaluate each expression exactly, and we're not to use decimal approximations at all. So we're going to really lean heavily on kind of the definitions of logarithms, right? That's the emphasis here in question 7. So, some of the things that you might have memorized or written on your note card are things that we've actually been using. I think these will be useful for us, right? Any log base b evaluated at b, right? What was that equal to? Um, right, so that was equal 1, right? Okay, and so another useful thing that we're going to be using here is that the log base b of 1, right, is equal 0. Okay, so yeah, these would be great things to have memorized or to have on a note card if you can have a note card. Log base 7 of 7, it fits that parameter of log base b of b, and so we know that this is actually just equal 1 for the reason given here. Okay, and so for part B, they're asking us log base 15 of 1. Again, this looks like the second rule that we were talking about just now, that log base b of 1, any base b, is equal 0. So this one is actually just equals 0. Okay, and so moving down to part C. Part C, there's a couple ways to do this. I'm sure there's more ways than I'm thinking of. But this one's going to be a dismantling of this rule. So if I had log base b of some x value minus log base b of some y value, this is going to be log base b of the fraction, right? Or the division of the first value divided by the second value, right? And so in our scenario, we can do it this way, right? We can kind of pull this apart, do the reverse of this rule we were just talking about over here. And so this becomes log base 4 of the numerator of that fraction, and then minus log base 4 of the denominator, 16 of that fraction. So this is helpful, right? Because we know log base b of 1 is equal 0. So in this case, when it's log base 4 of 1, that's equal 0. So for this one, it might be helpful for the next term, right? We have minus log base 4, and it should be of 16, but it could be proved to be useful if we actually think about 16 as 4 squared, right? Right? Because that in that scenario, right, we know that the logarithm actually brings down the exponent and makes it our coefficient of the log, right? So we have log base 4 still, and that's of 4, right? Perfect. Well, this is great, right? We're actually now using these rules that we stated initially, that the log base b of b is equal 1. In our scenario, the log base 4 of 4 is actually equal 1. So we get 0 minus 2 times 1, which is just 0 minus 2. And this just, of course, is equal to -2. And I'll just briefly go through possible another way. Be cool. If you knew another way too, feel free to stop by and tell me. Right? Okay. And so in this scenario, right, I'm going to write this with a negative exponent, right? Um, I might take one extra step just to show what I'm talking about here. I'm saying, well, 16 in the bottom of the fraction is equal to 4 squared. So I'll have the log base 4 of 1 over 4 squared. And then, right, this becomes 4 to the power of negative 2. So some fun little algebra tricks there with negative exponents. And then again, using the property that logarithms bring down the exponents, we get this, right? Negative 2 times log base 4 of 4, which this is just equal negative 2. So it's just another way of looking at this. I just wanted to show there are definitely multiple ways of thinking about these things. And so it kind of gives you the allowance to be creative in how you solve these. Okay, so moving on to part D. This one is actually pretty straightforward if you remember that the argument, the thing inside the logarithm, has to be greater than 0. And in this scenario, right, when we plug in negative 3, that negative 3 is not greater than 0, right? So this one, actually, we can just say, we can't evaluate it. It doesn't exist. So you can write DNE if you want. You can give the motivation as to why you said that it doesn't exist because the argument has to be greater than 0 inside a logarithm. So whatever you prefer on that one. Okay, so let's scroll down here to part E. Okay, so part E, it looks like we have two logs with the same base, and they're being subtracted. So if you remember the rule, let me scroll back up here so we can see it. This rule here, right, is this same scenario. And so we can actually just write this expression in part E right away with one log, right, of base 5. And it'll be a fraction, right, of this. So I'll just, to save time, I'll say, well, this is equal log base 5 of 5 squared over 5 to the 11th power, right? Well, actually, I don't think I like this, right? This is actually good to show you, right? The point here is to simplify this, and I think I'm not doing a great job at that. So let's go ahead. Well, I could keep going this direction. Shucks. Yeah, let's keep going in this direction. I think it's a good lesson for both of us. We can think on the fly, can't we? And so this will rely on some algebra skills with exponents if you went about it this way. Remember, if you're taking something, raising it to a power, and dividing that same thing raised to a power, we can subtract the exponents, right? And so this would actually become 5 to the power of 2 minus 11, right? That's one way of thinking about this. Yeah, not all is lost on this one, the way that I've approached it. Okay. And so, well, what is 2 minus 11? That's actually equal. I only have 2 and I'm taking away 11. So I'm left with negative 9 if I'm doing the mental math correctly today. Okay. And so again, logarithms, right? They're great because they bring down the exponent for us and they make them into those coefficients. So that negative 9 can come down and live on the outside. And we're just left with negative 9 times log base 5 of 5. Again, log base 5 of 5 is equal 1, right? So we have negative 9 times 1 or just negative 9. Great. That was a nice little one. Okay, so moving on to the last part of this question, part 5. Let's go ahead. This one, we have two logs with the same base, right? One of them has a coefficient of 2. We'll deal with that in just a sec. But they're being added. And so the rule we're going to use on this one, right? Addition of logs. So if I had log base b of x plus log base b of y, right? we could put this together as one logarithm, and that'll be log base b of x times y inside the argument there. But I have to do, I think, one step before applying this, right? Because let me deal with that 2 on the outside of the first term. Um, remembering kind of the reverse of what we just applied in part E, right? Remember we've been saying that the coefficient, or sorry, the exponents inside our logarithms can come down as the coefficient. So we're just going to reverse that rule on this one and throw that 2 back up into the exponential position. So this might be your first step on this problem. And then we have just the same on the second term, log base 12 of 3. Perfect. Okay, well, let's do two things at once, right? We're going to apply this rule over here on the right-hand side. I have addition between log base 12, 2 squared plus log base 12 of 3. So I can actually write this as one logarithm. And 2 squared is equal 4. And then it's going to be times 3, right, to apply that rule on the right. So, well, okay. 4 times 3, what's that equal? Yeah, 12, right? And so, all right, we've seen this rule, log base b of b, that's equal 1. So this guy just simplifies to 1, right? Perfect. Okay, moving on to question 8. All right, we've got a doozy of a little expression here, and we're asked to use properties of logarithms to expand it. Okay, so let's just get going on this one, right? One step at a time. So inside the logarithm, we have a cube root on the top of that fraction, things being multiplied underneath that cube root on the top of the fraction. Lots of exponents on these variables, and then we have division of y squared as well. So the way that I might start this problem is let me go ahead and just rewrite the original problem statement. Oops, that is not supposed to be a y, that's supposed to be a z. And make sure my radical sign goes over that. And then we have our y squared, right? So what I would suggest us doing first is to reverse the subtraction rule of logarithms, right? Since we're trying to expand this, we'll do some reversing of rules. And so we do the top of the fraction and then in one logarithm and then minus the bottom of the fraction in its separate logarithm, just like this. Okay, and so that would be my first step. I might just take a second to note, right? This is the cube root. I'm just picking x. Maybe I'll put a instead. The cube root of a can be represented as a raised to the power of 1/3, right? The exponential representation of this root can be, it can be written this way, the root can. So that means inside this guy, right, I have a exponent of 1/3, and lo and behold, the logarithm, right, brings out that exponent, makes it our coefficient. And so I'm going to bring down that 1/3, right? Just like that. Okay. And then the second term, this log of y squared, again, that exponent can come down in front as the coefficient. So got that guy there. Okay. And so what we have here in our first term, we still have x to the 5th power times z as the argument in that logarithm. We're going to reverse the addition rule of logarithms on this one. So we're going to have y 1/3 times log of just the x to the fifth in this one. And then we have to add, right? Since there's multiplication on the inside of the log, if I were to split those apart, I add, and just making sure, however you write it, make sure to also multiply this one by 1/3. We don't want to lose that. And then the -2 log of y, he's coming down as well. I think that one's all done and simplifying. Great. And so here, our second term looks like it's all done. Our third term on the 2 log y, that looks like it's all good. The first term, we have an exponent inside the log. And I think they tell us not to have any exponents, right? They say should not have any exponents or fractions um, on the variables, right? And so let's go ahead and pull out the exponent of 5. We know the logarithm brings that down in its coefficient. And so it can actually come down as just 5/3 now, right? Because 5 times 1/3 can be squeezed together to become 5/3. And now we just have the x as the argument of that first term of logarithm, our z here, and then -2 times log of y. All right. Don't think I'm forgetting everything there. I think that one's all done. Okay, let's move on now to question 9. All right. So it looks like it's almost like a reversal of what we just did in question 8, right? They're asking us to write the expression as a single logarithm. And we note all of the logarithms here, right, are base b. So we can totally combine these, right? And so we have initially log base b of z, right, plus 2 times log base b of y minus 4 of log base b of x, right? So I'll probably do the thing inside the parentheses first, right? So let me write down, copy back down this log base b of z. And so plus 2. Okay, so this guy, right, inside the parentheses, this log base b of y minus 4 times log base b of x. Um, it looks like I probably should clean up that second term first, right, before I apply the division rule of logarithms. And so let me rewrite this. Okay. And so that's becoming log base b of x to the fourth, right? That coefficient can go back up in the exponential position, right? Okay, and actually on this first term, that 3 log base b of z, let's go ahead and throw that 3 up into the exponent position. I didn't catch that the first time as we were going through this. So that can go up here. Okay, and so now this thing in the parentheses from above is ready to have the subtraction rule of logarithms be applied here. So we're going to do log base b of y divided by the second argument, which is x to the fourth, like that. And maybe I'll put parentheses around this to emphasize that's what's inside the logarithm, right? Okay. And so I do see addition, right, between these logarithms, but I need to deal with this 2 real fast, right? That 2 can be thrown up to the exponent of the argument of that second logarithm. And so let's go ahead and write that down real fast. Sorry, my Z's are getting kind of sloppy. And so we have log base b. It would be y over x to the fourth. You might know how this simplifies, but I'll go ahead and talk about that in the next step. Okay, so now we have addition of 2 logarithms with the same base. And so we can multiply the arguments, right? And write it as 1 log log base b. It'll become z cubed, right, times this guy over here, right? Y over x to the fourth, all of that raised to the power of 2. We might, write this in simplified form if you want, right? That exponent on the outside of this fraction can be distributed to the top of the fraction and the bottom of the fraction. And if you remember your exponent rules, if I have like x to the fourth raised to the power of 2, I'm multiplying those exponents, right? So a lot of rules being thrown around. And then, I guess obviously it just depends. This would be the final answer, but maybe I'll write it just once more. Maybe I won't. Maybe I'll mess up the B there, but so we have this guy. That might be my best final answer, and hopefully that one's correct for you. Perfect. Okay, let's go ahead and move on to question 10. See what's going on there. Okay, so question 10 has a few different parts, and they're asking us to solve the following equations. Um, yeah, so on this one, for part A, we're given something in logarithmic form, with the x that we're trying to solve for is inside the logarithm. So it actually would be favorable if we just switch this to exponential form. And so, right, what I mean by that is that this in part A, so log base 1000 of x is equal to 1 over 3. I mean, we could just take a second and think about what is the logarithm, right, indicating to us. So basically what it's saying is they're taking 1000 and we're raising it to the output here. And this is translating to exponential form, right? So 1000 is our base value. We're raising it to the power of 1/3. And we want to know what is that value inside the argument, that x, right? So this is that translation over to exponential form of the logarithm. So it'd be good to have that memorized or on your note card. Okay, so what we should do here, if it's not obvious, is we could think about this with our calculator and just punch this in if you wanted. The 1/3 exponent is actually representative of the third root. So I think we can logic our way through this. The third root is asking us what number times itself 3 times is equal to 1,000. So if you know your powers of 10, you might know that 10 times 10, well, that's equal to 100, right? And so if I had 10 100s, I would have 1,000. So 10 times 10 times 10 is equal to 1,000. So 10 is the number at which I can multiply by itself 3 times to equal 1,000. So here, x is equal to 10. Okay, moving on to part B. Let's see, what can we do with part B? I think in part B, actually, I might just try to take the log of both sides. And why not? Let's just do the log. This would be log base 10. That's what your calculator can do, as well as the natural log. But we did the natural log earlier. Let's do the log this time. And if I take the log of the left side, I'm going to take the log of the right side to preserve that relationship between these values. And so the logarithm, right, brings down that exponent. That's a great quality of it, right? Because now we have access to the exponent. It's now the coefficient of the log, right? Just like that. And then the right-hand side is still log of 7. Okay, and so here I want to know what x is, but x is being added to by 4, and then that quantity is being multiplied by log of 9. So to undo all of that stuff, I'm going to start by dividing both sides of this by log of 9. So I'm going to take the log of 7 and divide this by log of 9. And that's going to be equal. So if I divide the left side by log of 9, it just becomes 1. So this left side is just equal x plus 4. So I want to know what x is, but I know what x plus 4 is. So I'm going to subtract 4 from both sides of this equation. And I'll just get x on the left side. Let me finish here writing this. And then I'm going to subtract 4. So I would actually probably just throw this into my calculator. So let me see if I have a good result for that. I think I punched this into my calculator before, and I believe I got negative 3.11. All right, let's go on to part C. Okay, so part C. Um, this one actually, right, we're given a logarithmic form. And again, the x that we're trying to solve for is inside the logarithm. It's the argument or part of the argument, I should say, for this log. So it would actually serve us well to switch to exponential form. And so if you remember us doing that in this last problem, this can be translated. Let me if this is true, then this is true, right? We take our base and we raise it to the power of our output of this, which is 1, right? And then this would be equal to the argument inside the logarithm, that negative 3x plus 7. So this is the exponential form of what we're given in part C here. Okay, so right away, right, 4 to the power of 1 is just equal 4, right? So I could write it as just 4 if I want. Um, we notice on the right-hand side of this, right, that we are multiplying x by negative 3 and adding 7. So to undo all of those operations, I'm going to start by subtracting 7 from both sides of this equation. The left side would become 4 minus 7, and then the right side actually just has negative 3x, which is good, right? So here, 4 minus 7, that's equal negative 3, right? And then x is still being multiplied by negative 3 on the right-hand side. So if I divide both sides by negative 3, and that's supposed to be a fraction symbol, messed that one up a little. Then I would just have x on the right side, right? Because negative 3 divided by negative 3 is just equal 1. And so negative 3 divided by negative 3 now, right? That's actually just equal to 1, right? So I think we just found that x is equal 1, which if we wanted to, right, there might be a shortcut to this one, right? Um, if we remember that log base b of what? B is equal 1. Um, so what we would then see if we just to apply this, right? This would be a good thing, as we said before, to have memorized or on your flashcard. So directly now, this just says, I mean, it doesn't take away too many steps, right? But it gets us just to here, right? We're saying that this value on the inside, right, would have to equal this value of our base. The answer is still going to be the same, but it just kind of gets us there in a different way. So it's just kind of cool. Okay, so moving on to part D. Let's see, we have a bunch of natural logs of things, right? Let's go ahead and I think what I probably would do first on this one is it's just clean. I mean, I just see there's subtraction between two natural logs. So they have the same base, right? The base of E. Um, and so this can be rewritten. The left-hand side can be rewritten as x minus 6 over 10. I think I'm doing that right. You can correct me if I'm wrong. Perfect. Okay. So, we could, if we wanted, I probably would just actually say, well, if this were true, right? The natural log of x minus 6 over 10 is equal to the natural log of 5. I don't think it's too far-fetched for us to just observe that these arguments of these natural logs must be equal, right? Otherwise, they wouldn't be equal overall. Okay, so great. Now we've gotten to a place where there are no natural logs here at all. Um, and so in this scenario, I would actually see that x is being subtracted by 6, or 6 is being subtracted from x, and then divided by 10 on the left side. So to undo those things, I'm going to start by multiplying by 10 to undo that division, right? On the left-hand side, you'll see that that's just equal to x minus 6. And then the right side is just 50. Okay, and then x is being subtracted by 6. And so this becomes 56. We'll add 6 to both sides. Okay, so moving on to the last part of this question. We have log base 5, x plus 6 on the left side, and then we have another log base 5 on the right side. So I think it would be advantageous of us to probably just add the log base 5 on both sides of this equation to get it all over onto that same side. So I'm going to add log base 5 on this side, add log base 5 on this side, of course. Okay, and so the updated expression or equation is log base 5 of x plus 6 plus the log base 5 of x plus 2. And the right-hand side is just going to have 1 now. Okay, and so here we have addition between two logs with the same base. So we can write this as one logarithm, right, where the arguments are being multiplied. So we have x plus 6 times x plus 2, that second argument. This is all equal 1. So we can actually just we can switch this to exponential form like we did before. Um, or we can just observe, well, if this is true, that log base 5 of something is equal to 1, the argument here, or the something inside, this has to equal 5 in order for this to be true. So this is another way of thinking about it. It's always kind of nice to think about it in different ways. Right, so we'll just have that, oh, of everything inside just equal 5, and we're set, right? We got rid of the logarithm. And now this kind of just turns into a practice in expanding these things using FOIL, right? So I have first would be out x squared. The outside would be plus 2x. The inside would be plus 6x. So I think that between those two, I think I got 8x. Um, and then the last is just going to be 2 times 6, or 12. This is equal 5. And so I might subtract 5 from both sides at this point too. Okay, so let's go ahead. I'm running out of room down here. I'm going to bring it up and let's simplify this, right? I have x squared plus 8x, 12 minus 5. Those are like terms, right? That becomes 7, right? And so the reason why, and I guess I didn't highlight that, the reason why I did this, right, is because I subtracted the 5, that is, and set it equal to 0, because this is our protocol, right? If I had um, this second degree polynomial, um, in order for me to solve this, since there is that x term as well, I need to factor this. Even though we just came out of a factored form, I'm going to go ahead and factor it again. So uh, let's see. I want to think of two numbers that multiply together to equal 7, and that add up to equal positive 8. So fortunate for us, if you remember your prime numbers, Uh, Prime numbers, are only divisible by themselves and one. So 7 times 1 is the only way that we're getting to 7 with integer values. And 7 plus 1, right, is equal 8. And so let me just go ahead. I know it might be a review for some, but let me go ahead and just write out the full steps of what we might do here. So I'm rewriting the middle term 8x as 7x plus, and I'll put the 1x there just to emphasize this. Again, if you already know this, I apologize for the review, but this I'm going to kind of factor by grouping now. And so the first two terms, so these guys right here, I'm looking for the greatest common factor. The integer values, it's just there's a 1 here technically. Um, the integer values, they don't have anything in common except for 1, but the variables, there's an x in both of them, at least an x. And so I'll pull out an x. Right? And so I'm pulling out an x out of the x squared. There'll be an x left. And then pulling out an x out of the 7x, there's going to be a 7 left. Just like that. I'll close the parentheses, right? And now I'm thinking about on this one, right? Is there anything in common between the coefficients and the variables? Well, of course, the second term there, 7, doesn't have a variable, right? And we have been talking incessantly about the fact that 1 and 7 only have 1 in common. So maybe I'll pull out a 1 and emphasize that fact, right? And then what's left over is x plus 7 like this. Of course, this is all equal to 0. Okay, and so then I can see, well, in both of these terms, there's an x plus 7, right? Here it is, here it is. And so I can kind of pull those out, or however you like to think about it. In this first one, there's just going to be an X. In the second one, there's just going to be a 1 like this. So a little review there, right? The zero product rule says that if I have x plus 7 times x plus 1 equal to 0, then either x plus 7 is equal to 0, right? Or x plus 1 is equal to 0. Solving these, we see that x is equal to -7 and -1. But I will say this, right? When we're dealing with logarithms, you need to confirm that these are valid answers, right? Because obviously these are roots to this second degree polynomial, but we need to make sure that we can actually add these as arguments for our logarithms. So we have log base 5 in our original equation of x plus 6. So notice when I plug in -7 plus 6. Uh-oh, we have some trouble here, right? Log base 5 of -1. And, this is a no-go, right? Because the argument of a logarithm, this must be greater than 0. And, -1 is definitely not greater than 0. So this value will not work for our solution. And then we can just do a quick check. I'll do it a little bit different way for the -1 if we want. The arguments are both x plus 6 and x plus 2, right? These both have to be greater than 0. Just grabbing the arguments of the logarithms from the original equation. So this implies if we solve for x on this first one, that x has to be greater than -6 and x has to be greater than -2. And if we, thought about it for a sec, yeah, this one's good, right? X equaling -1 is greater than -2 and greater than -6. So um, final answer. I know I have it down there, but I kind of lost it with all my little lines. That would be my final answer for this one. Okay, moving on to question 11, kind of getting into the word problem section. Okay. So you can read this. The resale value of a travel trailer decreases exponentially every year since it was purchased. They give us this function for the model of this. V of t is the value at time t, where t is the number of years since 2002. Okay, so um, part A is talking about the y-intercept. And so, I mean, I always like to kind of think about this for a second, right? Kind of try to do a practical approach to this. And you may already know this. This is probably a review for most. I apologize. But um, if I'm living on the y-axis, if I'm hanging out here anywhere on the y-axis, right? What is always true about the x value, right? Well, we know coordinate pairs possibly. We know that if you're on the y-axis, your x value is equal to 0, right? So that is what we're going to use here, right? And so instead of x, we have t in this problem. So if we're on the y-intercept, you could probably actually also gain this in another way I'll talk about here in just a second. Probably be a better way, possibly. Actually, it ties back into what we were talking about before, but this is another way about it. This would be where t is equal to 0, and so we can just plug it into our function, right? Wherever there's a t, we plug in 0, and so we see that e to the negative 0.21 times 0, that's just 0. Well, anything raised to the power of 0 is just equal 1, and so this would be our y-intercept. Here's another way of looking at this that I totally just missed, but we talked about it initially, right? It actually will be helpful, I think, for the next part or second part from here. Um, you might think about like the parent function of this, right? Totally a useful thing to discuss, right? Y equaling a times b to the x power. Well, in our scenario, right, the b value is e, of course, but actually more to my point, we know this a value here, right, which is 30,000. A is described as the initial value for this parent function. And so you could also come to it in that way and say, well, in our scenario, A is equal 30,000. And because you know these exponential functions, that this is the initial value. There is a connection between the y-intercept and the initial value, and I'll let you kind of think on that. But this is how you might do that. Oh, and we are supposed to write a sentence explaining its meaning. Actually, more to what this question is actually asking us. Sorry. Um, so, yeah, what is this question asking us, right? This would be, oh, actually, I was just pointing it out. Hey, lucky yes, right? I was describing A as the initial value, and that's exactly what we're dealing with, right? Um, this is the trailer's initial value. So you might say the trailer's initial value. Hopefully, I'm spelling everything right for you. The trailer's initial value is, and let's do the units, right? This is dollars, right? It's supposed to be a dollar symbol. 30,000. Perfect. Okay, moving on to part B. We are to use the model to determine how many years it will take since it was purchased. And remember, from the original question, I think that said 2002. Let me check that real fast. Yes, right here, since 2002. Okay, um, back to the question. Use the model to determine how many years it will take since 2002 for the travel trailer's value to reach $450. So let's see here. So the original equation says our initial value was 30,000. We're multiplying it by e, excuse me, raised to the power of negative 0.21. I don't know what the T is. In fact, they want us to tell them how many years. So I'm going to leave T as T. And let's see. We have our A value. Um, our A value, I think, is this, right? We want to know how long will it take to reach this 450. Okay, let me make sure I copied down the equation correctly. I'm kind of going off of memory here. All right, that looks good, right? Always good to check. Okay, so in this scenario in part B, we are trying to solve for t. T's hanging out up here in that exponential position. And we know we can gain access to it by taking the log, right? Though we are going to have to do a little bit of work here. First, let's go ahead and divide by 30,000 first. So we're going to divide both sides of this equation by this coefficient of the thing raised to the power of t. So it's going to do this, 30,000. Okay. And so the left-hand side, you go ahead and simplify if you'd like. I'll just leave it like that for now. And then the right-hand side, I'm going to leave a little space here because I want to talk about what we're going to do next. But we're just going to have this guy, right? 30,000 divided by 30,000. That's just nice. It simplifies to just one, right? Okay. And so um, we still need to get access to that t. And so we're going to take the log of both sides. And I think because this is base e, it's advantageous. Sorry, because there's an e represented here, right? It's advantageous for us to use the natural log, right? And you'll see why if you don't already here in just a second. Um, if I take the natural log of one side of this equation, that means I have to take the natural log of both sides, right? Okay, just like that. Okay, so one of the coolest properties of the logarithms, right, is that we can gain access to the exponent and it brings it down as a coefficient, right? That's a really cool aspect here of this, right? So let's go ahead and do that. Let's bring that exponent down and it'll live as the coefficient. Let me copy this down correctly here. So negative 0.21 times RT, right? And times the natural log of E. You might know what that is. Then the natural log, we just have the same thing on this other side, right? I feel like that could definitely be simplified. It probably been advantageous for me to do so. So I didn't have to keep writing it, but okay, so on the right-hand side, we have our t value, right? This is awesome. Right, t is now on the outside of the exponent, and so we can go ahead and solve for it like we always would with these variables, right? T is being multiplied by negative 0.21 and the natural log of e. Well, um, right, the natural log of e can be, I mean, if you don't see it, the natural log of e is equal to 1, right? But another way to see it is that the natural log is just a log with base e, right? So this is the log base e of e, right? And we know that that's just equal 1. So obviously it's advantageous for us to also remember that the natural log of e is just equal 1. Okay, so this guy right here, right? We can just say, oh, that's equal 1. Okay, so t is being multiplied by negative 0.21. And so to undo that multiplication, we're just going to divide both sides by negative 0.21. So I'm just going to write that t is equal. I've divided off the negative 0.21, so it's just t. And then on the natural log side, I'll have this. I think I'll get rid of this red arrow. And then I got to remember this is divided by, right? Divided by negative 0.21. Cool. Okay, so how much time is this, right? I don't know. Oh, actually, hey, I simplified this. 450 divided by 30,000. Apparently, I simplified this earlier, so I'll just write that down for fun. Apparently, that's equal to 3 over 200. So go me on my simplifying before. Okay, so we're using the natural log here. That is a function in your calculator. You can totally use that. And I'll say it's approximately, when I did this in my calculator, 19.9986. That's where I stopped on my decimals. I'm not sure what happens after that, but they are asking us how many years. So I might just round this, right, to whole numbers or integers, right? Integer years. So this 19.9986 can be rounded to 20 years, making sure to add the units. Okay. Um, you might answer it in a sentence saying something like, it will take 20 years for the trailer's value to reach $450. That would be a great answer for this one. Okay, so part C of this problem, right? We're asked to state the horizontal asymptote. Not only that, we need to write a sentence explaining its meaning in this context. So this is what I kind of was talking about earlier when we started this problem. If you remember, let me scroll back up. So one of the ways that we were solving question A is I was talking about kind of this parent function, right? This guy right here, right? And um, if you know your exponential equations pretty well, which this is good for studying or memorizing if you can, or writing on a note card. We know that the horizontal asymptote for this guy is equal to 0. And so our equation, this v of t, is not being added or subtracted. And so we know in a very similar way that our horizontal asymptote is v is equal to 0, right? So here, state the horizontal asymptote. That would be, v is equal 0. That would be our horizontal asymptote, right? Um, you might think about this as, t grows or grows in general. I shouldn't say exponentially. If it just goes off, right? Um, what does this mean, right? Well, we hope, right, that the things that we own don't become debts that we own, like this trailer's value will approach 0, but won't go below 0, and then we have to pay anyways. Writing sentence explaining the meaning. I was just trying to go through that. Um, but I would probably say something like, um, as time goes on, or however you want to say that, as t goes on or increases, the value, right? The value of the trailer, right? Right. And remember, this is approaching the horizontal asymptote, right? So the value of the trailer is approaching, if I can spell this right, approaching $0, right? Okay. So that would be my best interpretation of that. Um, let's go ahead and move on. Okay. So question 12 is talking about the Torres family and their daughter. They're saving for college, right? And so this is a key thing here, just actually in the first thing. They say, well, it's in 13 years. Okay. How much money should they invest now at an interest rate of 8% per year? Okay, I'll underline the 8%. And then they say, well, it's compounded continuously. That should remind us of an equation, right? Let me go ahead and write that down. I think it's the APERT equation, right? A equals P times E raised to the power of RT. Okay. And so, right, APERT. Okay, so it's compounded continuously. We just wrote down that equation. And in order to contribute, they want to contribute this amount, right? Okay, so what do all of these things mean? We know we have this equation about compounded continuously. Um, our, our A value here, right, should be the account value at a certain time t. And so that's what that A is, right? Our R value is going to be the interest rate in a decimal, right? So you might see, let's go ahead and write down R is equal to the 8% divided by 100, or we just move the decimal over to the left 2 positions. Let's see. I think it'd be advantageous for us to talk about T, right? T is kind of hidden on this one. T is going to be time. So the only time that we see, right, is this 13 years. And I think if you convince yourself, right, if they're starting now in this investing scheme, they want it to be done in 13 years, right? It makes sense that in 13 years, that's the amount that they want, right? Okay. So what is the p-value, right? The principal investment, right? Let's see. How much money should they invest? They actually say that, right? How much money should they invest? So this is the thing that we don't know. So it means that the A is the thing that we do know, right? And that was this thing right here that they want after 13 years, they want $7,500. Great. Okay, so got the recipe, this EPERT, got the ingredients. Let's go ahead and throw these things together. The A value again was that 7,500. The principal amount, I don't know what that is yet, times E, which is just a number, raised to the power of our rate, which is 0.08 times 13. Cool. Okay, and so on this one, right, we can actually, because our p-value is just hanging out there as a coefficient of that e raised to a power, we can actually just divide off the unnecessaries here, right? We can divide by this e raised to the 0.08 times 13. Divide, of course, both sides so we don't alter the relationship of these things. Okay, and so this over here, right, that all just equals 1, except for the p, of course. So we'll have p is equal to whatever this is, 7,500 divided by e raised to the 0.08. Try not to write two squished together, times 13. Okay, so I think I punched this into my calculator earlier. And so my calculator got 2,650.910. Just for clarity, I'm just writing out what my calculator looks like. Might vary from yours, but we would likely, right? They actually are telling us, right? Round to the nearest dollar. So this time they are telling us what to round to the nearest dollar. So this is going to be rounded to $2,650, right? 2,600, oh, $51. My mistake. Okay, great. And so, you might answer that in a sentence if you want, saying something like the Torres family should invest $2,651. Okay, moving on to question 13. Question 13 is talking about wind chill. And it looks like wind chill is a function of wind speed. And the units of the temperature or the wind chill is in degrees Fahrenheit. The speed is in miles per hour, right? This will be helpful for us to remember. Okay, and so in part A, they're saying we'll find the wind chill if the wind speed is 23 miles per hour. Okay, so in this one, actually, they're just saying, can you plug in 23, right? Because X was the speed in miles per hour, right? And we have a wind speed of 23 miles per hour. So we're going to go ahead and say, well, C of 23 is equal 18.9 minus 7 times the natural log of 23, right? And I think I plugged this into my calculator earlier. Get to it. Yeah, perfect. So my calculator is telling me when I just plugged 18.9 minus 7 times the natural log of 23 into my calculator, it gave me negative 3.04859. I think maybe I missed a 4 there. Let's put a 4 here. Okay. 5115. Anyways, this is going to be, rounded to the nearest degree, right? So this will be negative 3 degrees Fahrenheit using the units. So if you wanted, right, I would suggest if you can, right, the wind chill when the wind speed is 23 miles per hour, right, is negative 3 degrees Fahrenheit. So that'd be a good answer to that problem. Okay, so part B, instead of a wind speed, they give us a wind chill, right? They say the wind chill is negative 5 degrees, and what is the speed in miles per hour? Okay, and so our equation from before was that C of X was equal to 18.9 minus 7 times the natural log of X. We don't know what X is. That's the thing we're trying to solve for. But we know what C of X is equal, right? It's negative 5 degrees Fahrenheit. So let's go ahead and plug that into our equation, right? This thing will be equal negative 5. And we have 18.9 minus 7 times the natural log of X, right? Okay, and so let's see here. Probably looks like we're going to do something, right? Because we have, if you remember before when we were evaluating those logarithms, simplifying, our x is inside the argument here. So it might send off some clues that we might be switching to exponential form. But let's go ahead. We're going to probably have to shuffle some things around first. So let's see. Um, I can add 7, right, times the natural log of x to both sides. Let's start there. And I'm doing that because, I don't know, I just wanted to do it. Yours might vary, and so don't feel like this is the only way. And then I'm also at the same time going to add 5 to both sides. Why not? We're capable, right? Let's have some fun. So I got 7 times the natural log of x is equal to 18.9. These two, right? That just goes to 0. And then it's 18.9 plus 5. 18.9 plus 5 is equal to 23.9. Okay, and so dividing right now because I need to get my natural log of x by himself. Remember, I'm kind of thinking about switching over to exponential form, so it'd be advantageous to get the natural log by himself on one side. So dividing the left side by 7, right? 7 over 7 will just be equal 1. And then 23.9 divided by 7 is what I'll have on this other side for now. Okay, so remember, right? We talked about this a second ago, I think, that, and you might already know that the base of the logarithm is equal e, but right? The natural log of x is just shorthand for log base e of x. And so e is our base of this logarithm, right? And so what this question is asking us, right, is e raised to 20, oops, I can write this, 23.9 divided by 7. That's what x is equal to, right? Okay, and so x was our wind speed, right? And I don't know what e to the 23.9 divided by 7 miles per hour is. So I'm going to use my calculator to solve for that, right? Let's see. I put this in my calculator before. And what did my calculator tell me? Let's see. Oh, here it is. Okay, my calculator before gave me, of course, a big old number. Try not to bore you too much. Right, again, I just wanted to show how I might round this, right? Because they're saying we'll round to one decimal place, right? So I'm going to round that to 30.4, right? 30.4, and then use the units, right, that are specified, which I believe were miles per hour, right? You might answer this with a complete sentence. That's always a nice feature when you're working with word problems. You might say something like, for a wind chill of -5 degrees Fahrenheit, the speed of the wind would be 30.4 miles per hour. Okay, so I think that was everything for that question. Moving on now to question 14. Now they're talking about radioactive substance, and it follows a continuous exponential decay model. I think they actually give us that, but continuous exponential, we're kind of getting primed and ready for that. Okay, so now it's saying, well, its half-life is 22 minutes. That's going to be important. And then at the start of the experiment, there was 56.8 grams present. Okay, so these are all very important things. We'll keep these in mind as we move through this problem. Okay, so part A tells us to let T be time in minutes. That's good to know. That'll be our units since the start of the experiment. And let F of T be the amount of the substance. They don't tell us the units of the amount of substance, but we were given grams, so I'm assuming we're to do units of grams. We're asked to find an exponential function of this form, right? And they give it to us. F of t is equal to a times e to the b times t, right? Okay, so if you recall, right, we've been talking about this a little bit. Um, if you know your exponential functions well, you know that a is the initial value, right, or initial amount. Since they actually give us this, right? They don't give it to us and say this is the initial amount. They say at the start of the experiment, this is the amount that was present. And so we have to kind of draw the conclusion that that's what they're saying. That's the initial amount. So we could get that that's what that's equal to. Again, another way that you could do this, right, is well, when the experiment started, right, t was equal to 0, right? And so you could plug in 0 and say, well, that's just equal a because e to the b times 0 is just 0, and that whole thing is just equal 1. And when t is equal to 0, there's 56.8. So there's other ways of doing this. It's not just based off of memory. But we come to that same conclusion that a is equal to 56.8. Okay, so I think that's all set. We got our a value. Um, Now, how do we solve for our b value? So this is going to take a little bit of clever work here. They tell us the half-life, right? The half-life is 22 minutes. And so what that means, right, is after 22 minutes, or when t is equal to 22, right, that f of 22, or the amount left right, after 22 minutes is half the amount from the initial, right? So I don't know what this is yet. I'm just gonna say, well, it's 56.8. That was the original, right? And that's the half amount, right? Or divide that by two, right? I'll try not to fumble over my words. Okay, and so did I solve for this before? It looks like I may have done that. Yeah, actually. 56.8 divided by 2 is equal to 28.4. That'll save me some writing here. Okay, so this is helpful for us, right? May not immediately seem obvious, but what we've just found is a point that this exponential model crosses, right? The independent value is our t value, or our independent variable is the t. In this scenario here is it's 22. And then the output when you plug in 22, right, is the dependent. That's 28.4 grams. Okay, so this is going to be key to our solving for B. Let's go ahead and update our equation since we haven't done that yet. So f of t, right, is equal, well, we said our A value, we found that in a couple different ways about it, was 56.8. Our B value is unknown as of yet. And then our T value, of course, is our independent variable. So remember the point that we just found, 22 comma 28.4, we can actually plug that into our equation, right? 28.4 was the output, 56.8 times E. Again, I don't know what B is, but I know T is equal 22. And then, right, our thing we're trying to solve for, you've heard me say this before, thing we're trying to solve for is hanging out here in the exponential or exponent position. In order for us to gain access to that, we're probably thinking, oh, we're going to do some logarithm stuff. But in order for us to get there, right, let's go ahead and start by dividing by 56.8. So if you divide the right-hand side by 56.8, right, that all just goes to 1, and we're just left with E, it's supposed to be an E raised to the power of B times 22. And the left-hand side, 28.4 divided by 56.8, right? Um, if you do that into your calculator, it might feel like a coincidence, but there's actually a good reason, right? This is equal to a half. And you can actually just jump to this if you know, if you feel comfortable with that. Um, right, you could jump to this step given the information. But let's go ahead and move on. So our value we're trying to solve for is still in the exponent position, that b up there. So what we want to do is take the log of both sides. And since e is involved in this, again, it's advantageous for us to go ahead and take the natural log of both sides. So I'll have the natural log of 1 over 2 is equal to the natural log of e raised to the power of b times 22. Again, we've seen this before. Cool thing is that this comes down as the coefficient now, right? So let's go ahead and rewrite that. We'll have that the natural log, and I'm kind of running out of room here. Sorry, it's getting a little jumbled. Natural log of 1 over 2 is going to be equal to b times 22 times the natural log of e. I'll go ahead and write that down, but you know what that is, right? That's just equal 1, right? Good thing to have memorized or on your note card. Okay, so we have now the natural log of 1/2 is equal to b times 22. We can go ahead and solve for b, right? B is just being multiplied by 22. So to undo that multiplication of 22, we just divide by 22. And I'm going to go ahead and write my b on the left here, right? Because 22 divided by 22, that's just equal 1. And so we're left with b equaling the natural log of 1/2 divided by 22. Okay, and so we've solved for our a value before, right? We solved for our b value just now. So we can actually put this together, right? They're just asking us to find an exponential function of the form f of t is equal to our a value, which was 56.8, times e. And I think you could get away with plugging this into your calculator if you wanted to approximate this. I would probably just keep it as this for my b value. It's a little cumbersome, but it will be the most exact answers for the later problems here. But that would be, right, the model that's used to describe this situation. Okay, moving on to part B. It's asking how much will be present in 21 minutes. Excuse me. So of course they're giving us a unit of time. So this is a t value, right? T is equal to 21 minutes after the experiment has started. So what we're going to do is plug in 21 into our equation wherever there is a t. I'll show you what that looks like. And I'd be interested if we rounded or plug this into our calculator, that b value we just solved for, so you don't have to rewrite this. But this would be my style. If I were taking this exam, I would just keep it that most exact as I can. Okay, so yeah, this is how much is left, right? But it'd probably be more useful for us to punch this into our calculator to see what this is equal to, right? And so when I did earlier, I got this value 29.30904. I think that's where those decimals terminated, if I remember correctly on my calculator. Um, and so in the context of this problem, you might question, well, it doesn't tell me what to round to, but if you remember at the beginning, they gave us, let me scroll back up. They gave us the amount present initially as 56.8, and so they had it to one decimal place. I may just follow suit, right, and say, this will be rounded to 29.3 grams. And, they're not asking, but you might give it to them in a sentence saying something like, there will be 29.3 grams after 21 minutes. Okay, so moving on to question 15. I think this is the last question of this review. It's talking about a study that showed that Oregon honeybees population was decreasing exponentially. And again, I think they give us that equation later on, but I'm just going to underline that. It's good to remember. At the beginning of the study, the bee population is in a specific area is 210,000. Oh, okay. Let's see. Actually, I think we have another question after this. 2 years later, the same area population was this. Okay, so we'll write down later what these things mean. They want us to find an exponential equation of this form. F of t is equal to, and I'm going to go ahead and rewrite that. F of t is equal to a times e raised to the b t. Okay, so, and they're also saying to round to 5 decimal places. Okay. What are we rounding to 5 decimal places? I think we'll find out, right? That kind of probably sounds like what we're going to do with our b value, right? Kind of like what I was hinting on the last question. Okay, so if you remember, right, what do these values mean, right? Well, they say at the beginning of the study, right, that this is our initial value, right? 210,000. So you could, if you wanted, right? If you know your exponential equations well enough, right? We could say, well, A is equal to 210,000. If you don't believe me, plug in T equaling 0 into your equation, right? Of this, right? So F of 0, right, is equal to 210,000. I'll leave that to you to solve for your A if you need that extra evidence. It's totally cool if you do. Okay, and so here I'm going to update our equation to F of T is equal, well, 210,000. That was our A value. And I don't know what B is quite yet, right? Okay, so the next bit of information they give us is that after 2 years, right? So 2 years later, dun, 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 and so I'm gonna like say, well, two, right? Numerical two, representing that. The population in the same area was now this, about 180,300. So what I'm going to do then is to plug in 2 into my equation wherever there's a t, and the output, right, is the number of bees. That's equal to 180,300, right? So let's go ahead and write that down. 180,300 is equal to that 210,000, the A value, right? Times E. I don't know what B is yet. E is raised to the B times T, excuse me. And our T value is 2, right? Remember, it was up here. Okay. So again, it's a very similar story. We've seen it throughout this exam review. Our B is trapped up in this exponential position. So we should be thinking to get access to that, I'm going to use the lovely logarithm. We're going to do a little work first, though, right? As usual. Let's go ahead and divide by that A value, that 210,000 on both sides. And so on the right-hand side, right, all of this right here, that just equals 1, right, which is a good thing. I got E raised to the B times 2. And let's see, did I go ahead and simplify that? It doesn't look like I did. So I'll leave that to you to simplify the 180,300 divided by 210,000. I'm just going to bring it down for now. Right. Cumbersome as it is, but um, let's go ahead and look at this. Okay, so now E is by himself. It's still being raised to that power of B times 2. E is involved in this scenario. We know what to do, right? We're going to take the natural log of both sides of this equation, right? To gain access to that exponent, right? Because the natural log, right? We know well enough now that that thing comes down is now the coefficient. That's the really cool thing about logarithms, right? Okay, so let's go ahead and rewrite that, right? I'm going to have b times 2 times the natural log of e, right? That should look familiar, what the natural log of e is. Keep that in mind. Oh gosh, at the very least, I feel like I can get away with this. I hate to think on the fly, but I can drop some of this, I think. 2 of the zeros, right? Let's see. Hopefully I didn't mess this up. I don't know if I have a calculator within reach, right? And so we remember that the natural log of E, that's just equal to the log base E of E, which we know that the log base B of B is always just equal 1, right? Which is why we chose the natural log in this scenario when we were dealing with E. So let's go ahead and update. Notice that there's just multiplication by 2. That's what B is being done to, right? Or something that happens to B is it's being multiplied by 2. To undo that multiplication of 2, we're going to divide both sides by 2. And we find that B is equal, right? This natural log of 1,803 divided by 2,100 divided by 2. Let me grab my calculator this time just to make sure I didn't mess up our simplifying of that fraction. Okay, so 1,803 divided by 23. Sorry. Thank you for your patience. Okay, that's equal to that decimal approximation. This will be important here in a second. So I'll keep my calculator close because I think we're going to have to round some things, right? Cool. Okay, so this is what B is equal to. And again, kind of like with the question 14, I kind of carried around this cumbersome B value. But, right, if you remember on this one, they tell us to round to 5 decimal places. So now they're giving us explicit instructions to round this value to 5 decimal places. So I hope I did that before. I think it would be equal to this negative 0.07624. Okay, so I believe that's my B value rounded to 5 decimal places. Let's go ahead and write out because we found like our B value, we found our A value up here. Let's go ahead and plug it into the form thereafter. So f of t, if you remember, it was equal to A, 210,000 times e raised to our b value, which we rounded, times t, right? Whatever t is. This is any time t, right? So this is what they're after. Cool. Okay. And so I totally forgot there is a question 16. This is the last question, I believe. Okay. So moving on, question 16. The amount of money invested in a certain account increases according to the following function, where Y naught is the initial amount of the investment and Y is the amount present at time T. Okay, and they give us the little guy there, right? Y is equal to Y naught times E raised to the 0.045 T. They want us to know after how many years will the initial investment be doubled? And then we're asked to round that to 1 decimal place. Okay, so it might be advantageous of us to first think about what it means for this investment to double, right? For example, like if the initial amount was $10 invested, right? What would be double of $10? And my 10 looks a little scribbly. Um, right? What does doubling $10 mean, right? That means it turns into $20, right? Okay, think about that. What if why not is maybe $15? I don't know. I'm just picking numbers, right? Well, that's equal, if it's doubled, right, it's equal to 30. So maybe just think about what are we doing here? Well, in this initial one for 20, that was 2 times the initial amount, right? And in this scenario of 30, right, the way I think your brain is doing that is you're saying, well, that's 2 times 15. Okay, so after how many years will the initial investment be doubled, right? The initial investment is unknown. We just use some like practical examples to kind of dive into this and figure this out. Um, if the initial amount is Y naught, right? Y naught when it's doubled would just be equal 2 times Y naught, right? 2 times the initial value. That's when it would be doubled, right? The initial investment doubled is just 2 times Y naught. So this is equal to, right, the amount Y that's present at time T, right? So we're saying, well, Y is equal to 2 times Y naught. Okay. I hope that made sense. So what I want to do next, right, is set up this equation, right? The equation says, well, Y naught times E raised to the power of 0.045 I don't know, right? They actually want us to know. They want us to tell them, sorry, how many years, right? So I'm going to keep T here, right? Okay. And so what is this equal to? Well, this is equal to double the initial investment, right? Which we were kind of just putting together. That's equal to 2 times Y naught. Cool. Okay. So if you're with me now, right? Again, you're probably tired of me saying it, but our variable that we're trying to solve for is up here, right? We want to know what T is equal to, right? We're curious. So what we are going to do, right? Probably of no surprise, we're going to be doing a logarithm of some sort. A little work needs to be done first before we take the logarithm. And there's an E involved, so I think that log will be natural, right? So let's go ahead and get started. What we should do right away is go ahead and divide both sides by Y naught. So on the right-hand side, Y naught divided by Y naught is equal 1. That's what we wanted. So the right-hand side is just E raised to the power of 0.045 times T. On the left-hand side, we actually have Y naught divided by Y naught again, and that's equal 1. So what we have on the left-hand side is actually just 2. Okay, kind of cool, right? Okay, so now we're in a place where we can take the log because we still have our variable in our exponent position. We need it outside of there. So I would take the natural log, right? We've seen this work well for us before when we have E. So let's go ahead and take the natural log of both sides. Um, in this action, right, let's go ahead and just remind ourselves, this is really cool. The exponent comes down is now the coefficient of our logarithm. So let's rewrite that. We have 0.045 times t times the natural log of e, and this is all equal to the natural log of 2. Write that down as well. Okay, you've heard me say this before, right? We know this. The natural log of e, that's equal to 1. Cool. Okay, so now we see that's what's left, right, is that t is being multiplied by 0.045. And we want to know what t is, right? So let me go ahead. I'm running out of room here. So let's say t, right, is equal. We're going to divide both sides by 0.045. That means I have to divide this side by 0.045. And so t is equal natural log 2 divided by 0.045. And then it's likely that we're going to want to, right? They even tell us round to 1 decimal place. They're telling Aaron, don't do this. Go ahead and use your calculator to give me the t value, right? Okay, so when I punch this into my calculator and round to that 1 decimal place, I can talk. Yeah, I got 15. Oops, not a decimal. 15.4. And then it'd be good to attach units to your answer. 15.4 years. That's what I got when I punched it in my calculator. And then you, of course, can answer this in a full sentence if you prefer. But that's the answer that I got. Great. Okay, so that's everything. Let me make sure I'm not missing anything. Cool. That is all of the solutions for the test to review. Hope you have a good day.